Hi there, welcome to the second lesson in our series on magnetism. At the end of our previous lesson, I asked you to carry out an investigation to find out which materials have magnetic properties and which materials are non-magnetic. Have a look at these results and compare your observations to mine. I tried wood, plastic, paper, copper, gold and tin. None of these samples were attracted to the magnet. I found, however, that these coins, pins and iron filings are magnetic. If you look at my table of results, you will see that I have only a few magnetic materials listed, but lots of non-magnetic materials. You know, many people are surprised by these observations because they think that all metals are magnetic. Clearly, this is not true. I'm pretty sure that your tests led to very similar observations. So, which elements are magnetic then? Let me show you on the periodic table. Of the metals, the ones that have magnetic properties are iron, nickel, and cobalt. And more recently, scientists have found that some of the rare earth metals, like neodymium and samarium, also show some significant magnetic properties. In fact, some of the strongest magnets available today are NdFeB magnets. These were first produced in 1984. They contain the rare earth element neodymium, iron, and the semi-metal boron. A mixture of these elements is processed and baked in an oven. These ceramic magnets are then magnetized using electricity. Now, what about the nonmetals? Do any of these elements have magnetic properties? Surprisingly, oxygen actually has some magnetic properties. Isn't that incredible? Did you ever imagine that oxygen would be a magnetic material? There doesn't appear to be any pattern to predict which elements are magnetic and which are non-magnetic. And when the elements that we have identified combine, they form a whole variety of magnetic materials. But why do some materials have magnetic properties while others don't? This important question will be the focus of today's lesson. To answer this question, we need to look at the microscopic arrangement of particles inside materials to begin to solve the mystery of how a magnet works. By the end of this lesson, you should be able to use a microscopic model to explain the properties of magnetic and non-magnetic materials, and describe how magnets interact with materials and with each other. Let's begin by recapping what we know about the basic model of matter. You should recall that matter is made from very small particles. The smallest building block of matter is called an atom. Atoms of different elements have different size and mass. Remember, the atoms of each element have different numbers of subatomic particles. There are three basic subatomic particles in an atom: the proton, neutron, and electron. The proton is positively charged and the neutron is neutral. The protons and neutrons are found in the nucleus of the atom. They give the atom its mass. The electron is negatively charged. Electrons are not found close to the nucleus, but are contained in orbitals of different energy. The electrons are continually moving within these regions of space around the nucleus. And it is inside these orbitals that some of the answers to the questions we have about magnetism lie. But first, I must tell you about the man who entirely changed the way the scientific world thought about magnetism: Hans Christian Ørsted. Ørsted made his remarkable discovery on an evening in April 1820. He was setting up an experiment to show the heating effects of a new electrical battery called the voltaic pile to some of his students when he saw something very surprising. The needle of a compass that was lying on the table next to the battery jumped and pointed to the battery when it was in use. He repeated the experiment several times to be sure, but the results stayed the same. In Oersted's time, scientists had tried to find some link between electricity and magnetism, but had failed. His experiments now showed that an electric current creates a magnetic field, and electromagnetism was born. You may be wondering what this discovery has to do with our atomic model. Well, it made scientists realize that there must be a connection between magnetism and the movement of charged particles. And where do we find moving charged particles? That's it, inside the orbitals of the atom. The movement of the electrons around the nucleus creates small magnetic regions. We call these regions magnetic domains and represent them by an arrow. The one end of the magnetic domain is called a north pole. This is represented by the arrow head. The other end, the south pole, is represented by the arrow tail. You can think of these regions as millions of tiny magnets inside each element. This basic model of magnetism that is linked to the structure and nature of the atom helps us understand the magnetic properties we have observed so far. Let's start by looking at the magnetic configuration in a simple bar magnet. Inside any permanent magnet, the magnetic domains are all arranged in a very ordered manner. All the domains are aligned. This means that we can draw the little arrows all pointing in the same direction. It is important that you remember that every magnetic domain has a north pole and that the opposite end is a south pole, because this helps us understand how the overall polarity in a magnet is formed. Look, this part of the magnet is the north pole because the majority of the north ends of the magnetic domains shown as arrowheads are found here. And on the same magnet, this is a south pole. The magnetic domains found in this region are represented as the tail of the arrows. But what does all of this mean? Well, these poles interact with each other in a very particular way. And Aaron is standing by in the lab to show you exactly how they interact with a practical demonstration.
Hey there guys, you know what? I'm sure you've seen something like this before. When I take this magnet here with the red north pole, put it on the table and take another magnet, it's red north pole, and put it close to it. Let's see what happens. They repel each other. The red pole is running away from the other red pole. Now we say that the red north poles have repelled each other. But if I take the blue south pole and put it close to the red north pole, see what happens. They attract. So we say that the red north pole and the south blue pole, they're attracted to each other. Well, now I'm going to repeat the same thing, but this time I use the blue south pole. Put it on the table, take another blue south pole and put it close to it and see what happens. They repel each other. Now we say that the blue south poles repel each other. They don't attract. Now I'm going to take the red north pole and put it close to this blue south pole and see what happens. They're attracted. Well, could you summarize how magnets interact with each other? Right. Magnetic poles of the same type, they repel each other. But opposite magnetic poles, they attract each other. Back to you, Diasha.
I hope you now understand that these two ends of a magnet are opposite in their nature. We call something with two opposite ends a dipole. In the elements on the periodic table, the magnetic domains are arranged in a random manner throughout a sample of the element, like here. These randomly arranged domains cancel each other out. There is no region that is distinctly like a north pole or a south pole. But interesting things happen inside these elements when they are brought close to a permanent magnet. let's see if we can use our magnetic domain model to clarify the properties of magnetic and non-magnetic materials. When a permanent magnet is brought close to a non-magnetic material, like a piece of copper, the magnetic domains are not influenced by the magnet. They remain in their random arrangement. In our previous lesson, we learnt that magnetic materials are attracted to magnets and can become magnetized. Let's see if the model of magnetic domains can help to explain this behavior. Firstly, let's have a look at magnetic materials that have not been magnetized. Here, the magnetic domains are randomly arranged. This looks very similar to non-magnetic materials. But watch what happens when a magnet is brought close to this magnetic material. The magnetic domains change their arrangement and adopt the same arrangement as the magnetic domains in the magnet. This may be a temporary change, so when the magnet is removed, the domains again take on a random arrangement. But if a magnetic material is magnetized, the domains will be aligned like the magnets for a longer time. Do you see how the magnetic domain model shows us that a magnetic material becomes magnetized when all the magnetic domains inside a magnetic material align in the same direction, just like those in a permanent magnet, to form two opposite poles? This idea has some very interesting consequences that need to be tested. The question I want you to think about very carefully is this: is it possible to separate a north pole of a magnet from a south pole? Look very carefully at the model of magnetic domains while you are discussing this question.
Hey guys, I think I have an experiment that may answer your question. Have a look here. This magnet has been marked red on the north pole and blue on the south pole. Now I could just cut this magnet in between where the blue and the red meet. But how will I know which one is the north pole and which one is the south pole? Could you think of a way to identify the north pole of a magnet? Remember, magnetic poles of the same type repel each other, but opposite magnetic poles attract each other. Now let's go back to our problem of trying to separate the north pole from the south pole. Now I've cut this bar magnet here in two halves. I've got now a red part and a blue part. Now, do you think that this red part is going to be north pole on each side, or will the one side be north pole and the other side be south pole? You know what? Why don't you write a prediction down and see if you're right? Okay, let's test it. Now I've got both of my halves on the table here, but then I don't need to test this side here because it's the original north pole and I've done nothing on it to change it, but I need to test this side here, which I've cut. What I'm going to do is to take the red north pole, bring it close to this new side here, and see what happens. It attracts. Now this means that the cut red end is the south pole. Now I'm going to take the same north pole, bring it to the cut side of the blue south pole and see what happens. It's running away. Now this means that the cut blue end is the north pole, even though it's marked blue. So, what conclusions can we make? Can we separate the north pole from the south pole? Let's go back to studio and see if the model of the magnetic domains confirms our results.
Thanks, Aaron. That really helps a lot. Let's look at the model of magnetic domains again. Remember, these magnetic domains are tiny regions that are formed due to the arrangement of the electrons moving around the nucleus. In a magnet, the domains are all aligned, pointing in the same direction. So whenever I cut or break a magnet, the cut will be between some of these tiny magnetic domains. One side of the cut will always have an opposite pole to the other. This means that it is impossible to separate a north pole from a south pole. For your task today, I want you to draw a diagram. Show what happens to the magnetic domains when the north pole of a magnet is brought close to a magnetic material. In this lesson, we have examined magnetic domains on a microscopic level. In our next lesson, we will take a look at the effect of these domains on the space surrounding a magnet. Join me then. Goodbye.